In July 2016, I had the pleasure of participating in the Biannual Meeting of the International Quantum Structure Association, which was organized by the School of Management and the Institute for Quantum Social and Cognitive Science at the University of Leicester in UK. My talk was about how to extend the quantum formalism to address the measurement and entanglement problems. Now, I just found in my computer the PowerPoint of my presentation, and since it is actually a nice PowerPoint, even with some animations, I thought it was a good idea to use it for a video, telling again what I had explained during my speech. So here it is. I hope you will enjoy. There are many different ways to state and understand the famous quantum measurement problem, associated with many interpretations of the quantum formalism. However, most physicists, accepting the existence of individual entities, would agree that a quantum measurement involves the interaction of the measured entity with a measurement apparatus, and that only one among a number of possible outcomes can be obtained from such interaction. Therefore, most physicists would also agree that a key aspect of the measurement problem is that of understanding how and where the collapse or reduction of the pre-measurement state occurs, and why the Born rule can successfully predict the relative frequencies observed in the laboratories. A related question is, are quantum probabilities ontological, or do they appear as consequences of a condition of lack of knowledge? But then, lack of knowledge about what? Another fundamental issue in quantum mechanics, though less publicized than the measurement problem, is understanding what happens to the components of a composite entity when, following their interaction, they become mutually entangled. Indeed, in standard quantum mechanics, a composite entity can always be characterized by a well-defined state. However, if its components are entangled, apparently they can no longer be associated with specific individual states. In other words, two fundamental problems of quantum mechanics are: 1. Finding a coherent and general mechanism explaining the emergence of quantum probabilities, as described by the Born rule and the associated projection postulate. And 2. Explaining how a composite entity can exist when its components apparently no longer exist, at least according to the physical principle saying that if a physical entity exists, then necessarily it must be in a genuine, well-defined state. The main purpose of this presentation is to emphasize that these two problems are related, in the sense that a solution to both can be offered by suitably extending the standard interpretation of quantum theory. With this, I do not mean that new mathematical entities should be introduced to complete the standard quantum formalism. It will be sufficient to redefine the reach of some of the existing entities, which so far only received an incomplete interpretation. I'm here talking about the density operators, which I will simply call operator states. As opposed to vector states, also called ray states, operator states are not assumed to represent genuine states, as only vector states are given this role in the standard quantum interpretation. My point here is that this is a possible mistake that could be the reason why the above two problems have not received so far a convincing solution. In other words, there are reasons to believe that the mathematical representation of genuine states, describing the objective and not subjective condition of a physical entity, I mean its reality in a given moment, should be generalized to also include the operator states. There are in fact many clues already suggesting that operator states are more than mere representation of classical statistical mixtures, and one of them is that a same operator state is able to represent an infinity of different statistical mixtures. But okay, since the proof is in the pudding, my task in this presentation is to show that if we assume that density operators also represent genuine states, and more precisely those operator states that an entity can enter in during a measurement process, then the wave function collapse can be described as a physical process which is similar to a symmetry breaking, and that, consequently, quantum probabilities can be understood as epistemic statements expressing a condition of lack of knowledge about which specific measurement interaction is selected at each run of a measurement. For this, let me start considering the simplest conceivable situation, that of a two-level system. In other words, I start by considering a two-dimensional quantum entity in the so-called Bloch representation, which uses a three-dimensional unit sphere. In standard quantum mechanics, pure states are the points at the surface of the Bloch sphere, and they can be described using the three traceless Pauli matrices. The so-called classical mixtures are instead the points inside the sphere. On the other hand, in the extended Bloch representation, all points of the Bloch sphere, those at the surface and those in the interior, are representative of genuine states, as also the latter describe, as we are going to see, a true potentiality aspect of the system. Consequently, movements going from the surface to the interior and return can describe bona fide physical processes, during which the physical entity always remains in well-defined states. Let me now show how this extended Bloch representation can be exploited to also describe measurement. To this end, let us focus on the eigenstates of the observable that is measured. More precisely, let us consider a self-adjoint operator O with a given spectral decomposition. The two-dimensional complex eigenvectors being orthogonal, one can show that the two three-dimensional real vectors representative of them in the Bloch sphere, n1 and n2, must point in opposite direction. In other words, they both lie on one of the diameters of the Bloch sphere and correspond to the two vertices of a one-dimensional simplex of length 2. As I will explain, this describes within the Bloch representation the potentiality region associated with the measurement of the observable represented here by the operator O, in the sense that each point lambda in the one-dimensional simplex, in the diameter in question, can be associated with a different measurement interaction, able to bring the initial state vector to one of the two outcome state vectors, here n1 or n2. To explain what I mean with this, let me recall that, following the standard description, the vector representing the state of the entity in the Bloch sphere should always remain on its surface. It is not allowed to immerse into it. This because the points inside the sphere would only describe conditions of subjective lack of knowledge about the actual state of the entity. On the other hand, according to our working hypothesis, inner points can also represent genuine states, and precisely those missing states that are needed to describe what happens behind the scenes of a quantum measurement. Now, to help visualizing the measurement process, let me associate an abstract point particle to the initial state vector r. In other words, we do as if r would be the Euclidean position vector describing a point particle, initially located somewhere on the surface of a Bloch sphere. We can also think of the one-dimensional simplex subtended by the two outcome state vectors n1 and n2 as if it was made of a substance able to exert an attraction towards the particle, causing it to enter the sphere region, following a rectilinear path orthogonal to it, until it comes into contact with the latter and remains firmly attached to it. This diving movement is only meaningful because we have hypothesized that also the internal points can represent genuine states, which means that by entering the sphere, the physical entity always remains in well-defined states and therefore never ceases to exist. Now, let us think of the potentiality region as a uniform elastic band that, sooner or later, will break, at some point lambda. All points of it are potential breaking point, and each breaking point can be associated with a different interaction between the elastic and the point particle. So when this happens, when the elastic breaks, here in a point between the position of the particle and N2, by collapsing, it will bring the particle towards N1, which is the final outcome. Let us repeat the process once more. The particle falls, the elastic breaks. This time it is in the region between the particle and N1. And by contracting, it brings again the particle to its final state, the outcome state of the measurement, which this time is N2. Now, what are the outcome probabilities? Here we observe that all these breaking point interactions are equally available, as nothing in the formalism favors one instead of another. In other words, there is an initial symmetry, which will be broken because the system is forced to produce an outcome. In our description, this is because the elastic is put under tension, and since it is breakable, at some point it will break. How this happens depends, of course, on the external fluctuations, corresponding to the asymmetrical cause required by Curie's principle, a cause that needs not be explicitly described in the theory. Instead, what the theory needs to indicate is the proportion of interactions that can produce each outcome, as from this proportion the outcome probabilities can be deduced, which means that the process we are here considering, when viewed from the perspective of the outcome, is a weighted symmetry breaking process. So, if the elastic, the one-dimensional simplex describing a diameter of the sphere, is assumed to be uniform, that is, each potential breaking point is assumed to have the same probability to become an actual breaking point, and considering that the first stage of the measurement is perfectly deterministic, one finds that the transition probabilities are exactly those predicted by the quantum mechanical Born rule. Coming back to the diving movement, the plunging into the sphere, as I already emphasized, it is a physically meaningful process because also the internal points can represent genuine states. But what happens when the particle representative of the state of a quantum entity reaches the potentiality region? Well, one can show that when this happens, the state changes in such a way that the off-diagonal elements of the operator state, with respect to the measurement basis, gradually vanish, so that the final unsimplex state becomes a fully reduced operator state. Note, however, that here we do not take any specific position with regard to the nature of the physical process that would produce the above change in the operator state, or in the density matrix, if you prefer. For example, one could say that the vanishing of the off-diagonal elements results from an immersion of the physical entity in a heat bath, following decoherence theory, or that it results from the interaction between offer and confirmation waves following the narrative of a transactional interpretation of quantum mechanics. What is important to keep in mind is that the operator state is not here to be interpreted as representing a statistical mixture expressing our ignorance about whether the entity is in one pure state or another. The unsimplex, fully reduced operator state expresses here an objective condition of a quantum entity coming into contact with the potentiality region, subtended by the measurement. In other words, it represents a bona fide pre-collapse state. Summing up, during a measurement process, the measured entity, initially in a vector state, accesses the interior of the Bloch sphere, going through different density operator states. The first deterministic stage of the measurement is a decoherence-like process. Then, a collapse-like process follows, which is a weighted symmetry breaking process, where the cause of the symmetry breaking is the actualization of a potential measurement interaction. Good. What I have just shown is how to extend the standard Bloch sphere representation to include also a description of the measurement, as weighted symmetry breaking processes operating at the non-spatial level of the hidden measurement interactions, which are assumed to provoke the change of the state of the entity, in accordance with the Born rule and the projection postulate. However, one may wonder whether this abstract point-particle representation and the associated elastic braking mechanism are just an anomaly, considering, for instance, that Gleason's theorem notoriously holds only under the restriction that the dimension of a Hilbert space is larger than 2. This possible objection, and similar ones, is however unfounded. Not only because Gleason's theorem can be shown to also apply to qubits, if the probability measure is, for instance, assumed to be continuous, but more importantly because the Bloch representation can be generalized to Hilbert spaces of arbitrary dimension and to measurements having an arbitrary number of outcomes. This is done by observing that the Pauli matrices are free generators of SU2, the special unitary group of degree 2, and that one can introduce a determination of the generators of SUn, the special unitary group of degree n. These generators, which are now n squared minus 1 in number, like the Pauli matrices, are Hermitian, traceless, and mutually orthogonal, and can be normalized similarly to the Pauli matrices. This means that any operator state can be represented in their basis, and the main difference between this generalized Bloch representation and the standard one, apart the obvious increase in the number of dimensions, is that not all vectors in the Bloch hypersphere, which is now n squared minus 1 dimensional, are representative of states. However, all vectors representative of bona fide states fill a closed convex portion of it, whose shape depends on the specific choice for the generators, with the vector states always corresponding to the points at the surface and the operator states to the inner points. To extend the previous description of a qubit measurement to the general n-level situation, one can consider an observable represented by a self-adjoint operator O with a given spectral decomposition. The orthogonality of the complex n-dimensional eigenvectors now implies that the corresponding n squared minus 1 dimensional real Bloch vectors are now the unit vertex vectors of a n minus 1 dimensional simplex inscribed in the sphere. In other words, simplexes naturally emerge from the Bloch representation of states as a geometric structure associated with the description of a measurement context. For n equal 3, we have an equilateral triangle inscribed in an 8-dimensional sphere. For n equal 4, a tetrahedron inscribed in a 15-dimensional unit sphere, and so on. Hence, only for the n equal 2 case we can fully represent the state space within the 3-dimensional Euclidean space. For n equal 3 and n equal 4, we can still represent within the Euclidean space the potentiality region, the simplexes being 2-dimensional and 3-dimensional, but not the full convex region of states, as they are 8-dimensional and 15-dimensional. And of course, for n strictly greater than 4, every aspect of the measurement requires more than 3 dimensions to be visualized. Now, similarly to the n equal 2 case, also in the general n outcome case, the point-particle representative of the state first plunges into the sphere, or more precisely into the convex region of states inscribed into the sphere, along a rectilinear path orthogonal to the measurement simplex, producing the unsimplex pre-collapse state vector. Let us show how it works for the 3-outcome case. The initial state of a physical entity lies on the surface of the 8-dimensional generalized Bloch sphere. The triangular membrane, the 2-dimensional simplex, associated with the measurement, is stretched over the 3 points n1, n2, and n3, the vertex vectors representative of the outcome states. The particle, attracted by the membrane, orthogonally folds onto it and reaches its on-membrane position, and in this way it gives rise to 3 distinct convex regions separated by tension lines. The disintegration of the membrane then starts in a random point, in one of the 3 regions, Here it is the one delimited by N2, N3 and the particle. This causes the detachment of its two anchor points, and the contraction of the membrane brings the point particle to its final location, here N1, representative of the outcome of the measurement. What about the outcome probabilities? As for the n equal 2 case, the sizes of the three regions can be assumed to describe the number of the available measurement interaction, so that the transition probabilities are given by their relative area. And this means that, again, the Born rule can be derived and understood as resulting from a weighted symmetry breaking process over the available hidden measurement interactions. And all this also holds for the 4 outcome case, the 5 outcome case, and the general n outcome case. But let us now use this extended and generalized Bloch representation to model quantum entanglement. For simplicity, let us limit ourselves to the 2-qubit situation, which means that the Hilbert space is 4-dimensional. So we need 4 square minus 1 generators, that is, 16 minus 1 equals 15 generators. The entity being composite, it is natural to introduce a tensorial determination of the generators of SU4. More precisely, considering that the trace of a tensor product is the product of the traces, it is possible to construct the 15 generators of SU4 as the tensor products of the 3 generators of SU2 plus the identity operator. By doing so, one obtains, by direct calculation, that the vector R associated in the extended Bloch representation with an entangled vector psi possesses a simple tripartite direct sum structure, where the first 2 vectors in the direct sum, Ra and Rb, are the 3-dimensional Bloch vectors associated with the operator states representing the individual state of the 2 entangled entities, and the third vector, which is 9-dimensional, is that part of the vector state describing the potential correlations between the 2 sub-entities. So, different from the standard formalism, the extended Bloch representation allows to describe an entangled state as a condition in which the 2 sub-entities are always in well-defined states, represented by the 2 vectors Ra and Rb, with their interconnection being described by a third vector, a correlation vector, whose components cannot be in general deduced from those of the 2 sub-entities, in accordance with the principle that the whole is greater than the sum of its parts. And let me also mention that this direct sum representation of entangled states also holds and generalizes for arbitrary n-partite systems. But let me conclude now by considering a situation where the effects of the correlation vectors can be easily visualized by means of a rigid rod connection between the 2 points particle. For this, we assume that they form a single state, which means that the 2-point particles are initially both at the origin of their Bloch spheres. Entanglement can then be modelized by simply considering that the 2-point particles are connected via an extendable rigid rod moving on a pivot. We then consider the measurement of a spin product observable, with Alice measuring her spin along direction Na+, and Bob along direction NB+. So these are the orientation of their Stern-Gerlach apparatuses. Since it is a tensor product observable, the coincidence measurement can also be decomposed here in a sequence of 2 one-entity measurements, with the order of the sequence being irrelevant. So let us see how it works. Let us assume that Alice executes first her measurement. This means that her elastic breaks first. Here it happens in a point such that her particle is drawn to Na+. This will happen with probability 1/2, since it was initially at the center of the sphere. Now, because of the rod connection, Bob's particle is then forced to transition to the state represented by Na-. At this point, the rod connection is disabled, and Bob observable is also measured. So his particle also falls onto the elastic. which then also breaks, here in a point in the line segment between NB minus and the on-simplex position of the particle. The collapse will then produce the outcome NB plus, and of course a statistically equivalent process can be described starting with Bob's measurement, and by doing the calculation, one recovers the exact Born rule predictions and the exact 2 square root of 2 violations of Bell's inequalities. So, I have tried here to deflate two fundamental problems of quantum mechanics: the measurement problem and the entanglement problem. A key ingredient for the deflation of both problems is the addition of a new typology of bona fide states to the standard formalism, represented by the density operators. These new states are different from the usual states represented by unit vectors, as they are never eigenstate of a self-adjoint operator, and hence contain an irreducible probability whenever tested. More specifically, they can only give rise to outcome probabilities different from 0 and 1 in all measurements, and in that sense, they should be considered to belong to a perhaps deeper and more hidden layer of our physical reality. It is this more hidden, non-spatial layer that quantum entities would enter when interacting with a measuring apparatus, which would explain how a collapse can possibly occur. The latter, strictly speaking, would not be a discontinuous jump-like transition from a pre-measurement vector state to an outcome vector state, but a continuous transition in the extended operator state space where the entity passes through different operator states before reaching the final outcome, following a weighted symmetry breaking process. This more hidden layer would also be inhabited when quantum entities become entangled, that is, when a non-spatial, non-local connection is established between them. Within traditional quantum theory, where operator states are only allowed to be interpreted as classical mixtures, there does not seem to be a straightforward way to experimentally test for the existence of these extra genuine states. This, however, does not mean that in the future their existence will not be highlighted by some indirect means, even experimentally. So, as the French say, affaire à suivre. Thanks for your attention.